We also said that the group 3 cations will eventually precipitate out as we raise the pH. So the next part of this particular question will be, at which pH will FeS precipitate using our experimental conditions? So we can actually calculate the pH at which this will precipitate out at. So our Q expression can be set equal to the KSP, which is going to be 6 times 10 to the minus 19. That's going to equal the concentration of the Fe2 plus times the concentration of the HS minus times the concentration of the OH minus. And remember, if we want Q to be greater than K, we want these concentrations to be increased. Both the OH minus and the HS minus are going to depend on the pH. So each of these two concentrations right here depend on pH. And once I write out this expression here, I'll show you how by increasing the pH we'll make Q larger in each case. So our Q expression is going to be equal to the metal ion concentration, which is 0.01, times the HS minus concentration. If we write this out longhand, it's going to be 9.5 times 10 to the minus 8 times the concentration of the H2S, which is 0.1, divided by the concentration of the H plus. Here the H plus is in the denominator, so as we raise the pH, that H plus goes down. So if that concentration goes down, we're going to make that quantity in brackets larger. We also know that the OH minus concentration is going to be the Kw divided by the H plus. This we will set equal to 6 times 10 to the minus 19th. So if you're looking for a formula, you can always generate this formula right here based on given information. Okay? But this formula right here will allow us to calculate pH, because what we can do now is we can solve for the H plus concentration, and that will allow us then to calculate the pH. So in this particular expression, if we multiply everything out, we're going to get 9.5 times 10 to the minus 25 divided by the H plus concentration squared is going to equal 6 times 10 to the minus 19th. If we do the algebra and solve for the H plus concentration, this is going to give us 0.00126. If we take the negative log of that, we can get the pH, which is going to end up to be roughly 2.9. So this pH right here is the pH at which FeS will begin to precipitate. So what does this mean in terms of what we're looking at in our particular laboratory? This is going to allow us to separate out, and doing these pH calculations will allow us to separate out various ions in solution. Because in this particular case, if we look at iron sulfide, and this is a pH scale, we know from our calculation that a pH of 2.9 is going to be the separation point between where iron is in ions in solution and when the iron sulfide begins to precipitate out. So in this case, if our pH is below 2.90, we have Fe2 plus in solution plus all of our other thioacetamide and saturated H2S solution and all that kind of stuff. But as we make this solution more basic, iron sulfide is going to begin to precipitate right when the pH goes above 2.9. If you look at the homework set on Carmen, you can do all the pH, or you can calculate all the pH values at which all of these metal cations will precipitate out. Okay? So this will allow us then to use these pH values to either put a particular ion in group 2 or to put a particular ion in group 3. And furthermore, we can take those separations and we can calculate at which the pH of each of these sulfides will precipitate out. All right? So does anybody have any questions on this particular analysis right here? Essentially what we do is we can figure out approximately what our metal ion concentration is in our test tube. Okay? In the particular lab that you're performing, that metal ion concentration is roughly 0.01 molar. We also have a saturated solution of H2S. That's going to give us a concentration of 0.1 molar. The variable that we have that we can control is we can control the pH. By manipulating the pH, we can manipulate two steps, or two concentrations in the Q expression. The hydroxide ion concentration is very straightforward, but the HS minus concentration is also going to be influenced by the pH because you're going to shift that equilibrium. In both cases, by raising the pH, it's going to make that Q value larger. So we can look at the instances where Q becomes greater than K for each of our experimental conditions. And this allows us to be able to separate each of these two. So make sure that you take a look at the homework set that's posted on Carmen and go through each of those examples. And then I believe there's a chunk of like 4 quiz questions at the very end. 2 of them deal with this sulfide solubility precipitation, and 2 of them deal with some problems from the other lab. On Wednesday, we're then going to start with our transition metal unit and talk a little bit more about what happens when these complex ions form.